Imagine visiting 5 pharmaceutical manufacturing plants. Every plant has a reactor. Every reactor performs mixing. But when you look inside, one reactor has an anchor agitator. Another uses a pitched blade turbine. The next uses a Rushton turbine. Another uses a hydrofoil. And one reactor even uses a retreat curve impeller. If every reactor performs mixing, why aren't they all using the same agitator? Is one agitator better than the others? Or does each one serve a different purpose? Today, we'll answer one of the most important questions in process engineering: how do engineers select the right agitator? One of the biggest misconceptions is that better mixing simply means increasing the RPM or installing a larger agitator. But that's not how process engineering works. The best agitator is not necessarily the fastest. It is not the largest. And it is certainly not the most expensive. The best agitator is the one that creates the flow pattern your process actually needs. Because different processes require completely different types of mixing. Before discussing different impellers, we first need to understand the language of mixing. Every agitator moves liquid in a particular direction. That movement is called the flow pattern. Most industrial agitators produce one dominant flow pattern: axial flow, radial flow, or tangential flow. Once you understand these three flow patterns, choosing the right agitator becomes much easier. Let's begin with axial flow. In axial flow, the liquid moves parallel to the shaft of the agitator. Typically, from the top of the reactor toward the bottom, before circulating back upward. This creates excellent bulk circulation throughout the vessel. Axial flow is ideal when the objective is to move the entire liquid volume. That's why it's widely used for liquid blending, solid suspension, heat transfer, and many general-purpose chemical reactions. Many commonly used impellers, such as the pitched blade turbine, hydrofoil, and marine propeller, are designed to produce predominantly axial flow. Now let's look at radial flow. Here, the liquid leaves the impeller horizontally, toward the reactor wall. When it reaches the wall, it changes direction and circulates through the vessel. Radial flow creates intense local turbulence. This makes it extremely effective for gas-liquid mixing. Consider a hydrogenation reaction. Hydrogen enters the reactor as large bubbles. To achieve efficient mass transfer, those bubbles must be broken into thousands of tiny bubbles. A Rushton turbine generates high shear, helping to disperse the gas and increase the contact area between hydrogen and the liquid. That's why radial flow impellers are commonly used in hydrogenation, oxidation, and fermentation processes. The third type is tangential flow. Here, the liquid primarily moves around the circumference of the reactor rather than vertically or horizontally. At first glance, this may appear to provide weaker mixing. But for highly viscous materials, it's exactly what's needed. Think of mixing honey, toothpaste, resin, or pharmaceutical creams. These materials don't flow like water. If a high-speed turbine is used, only the liquid near the impeller moves, while the rest remains almost stationary. This creates dead zones and poor heat transfer. An anchor agitator, however, slowly sweeps the liquid close to the reactor wall, continuously bringing fresh material into contact with the heating or cooling jacket. This improves temperature uniformity and prevents stagnant regions. In highly viscous systems, the objective isn't high turbulence. It's efficient movement of the entire viscous mass. We've now learned the three fundamental flow patterns used in industrial mixing. Axial flow provides excellent bulk circulation. Radial flow creates high turbulence and efficient gas dispersion. And tangential flow is ideal for highly viscous materials. But here's an important question. How do engineers create these different flow patterns? Is every agitator capable of producing all three? Or is each agitator specifically designed for a particular purpose? Let's find out. Now let's think like a process engineer. Suppose you've developed a new chemical process. The reactor hasn't even been designed yet. Would you immediately say, I want a PBT? Or, I want a Rushton? Of course not. The first question is, what does the process actually need? Does it require rapid blending, efficient heat transfer, gas dispersion, solid suspension, or gentle mixing for crystallization? Once those requirements are clear, the required flow pattern becomes obvious. And once the flow pattern is known, selecting the right agitator becomes much easier. Let's look at some real process scenarios. Imagine you are designing a reactor for a general chemical reaction. The viscosity is low, no gas is involved, but the process requires good circulation, efficient heat transfer, and reliable solid suspension. Which agitator would you choose? The answer is the Pitched Blade Turbine, commonly known as the PBT. Why? Because these requirements demand axial flow. The angled blades continuously circulate liquid throughout the vessel. Fresh reactants are distributed quickly. Solids remain suspended. Temperature becomes more uniform. That's why the PBT is often considered the workhorse of the chemical industry. Now consider a hydrogenation reaction. Hydrogen enters the reactor as gas bubbles. The catalyst is suspended in the liquid. The chemistry is correct. The temperature is correct. The pressure is correct. But the reaction is progressing slowly. Why? Because the limiting step isn't chemistry. It's gas-liquid mass transfer. Large hydrogen bubbles escape before enough gas dissolves into the liquid. A Rushton turbine solves this problem by generating strong radial flow and high local turbulence. Large bubbles break into thousands of tiny bubbles. The gas-liquid contact area increases dramatically, and the reaction becomes much more efficient. Now imagine manufacturing a polymer, a resin, or a pharmaceutical cream. As the batch progresses, the viscosity increases dramatically. Would a high-speed turbine still work efficiently? Not really. Most of the liquid near the impeller moves, while material near the reactor wall barely circulates. Heat transfer becomes poor. Temperature gradients develop. This is where an anchor agitator is the preferred choice. Its large diameter continuously sweeps the reactor wall. Fresh material is brought into contact with the heating or cooling jacket. The result is improved wall heat transfer and more uniform temperature throughout the batch. Not every process requires high turbulence. During cooling crystallization, the objective is to grow large, uniform crystals. Too much shear can continuously break growing crystals into fine particles. These find slow filtration and increased drying time. That's why engineers often select a Retreat Curve Impeller, which provides gentle circulation while minimizing crystal damage. Now consider a completely different application. A large storage tank blending two compatible liquids. There are no gas bubbles, no crystals, no highly viscous material. The goal is simply to circulate a large volume of liquid while consuming as little power as possible. In this case, a hydrofoil impeller is often the better choice because it provides excellent circulation with lower energy consumption. By now, you've probably realized that selecting an agitator isn't just about mixing. It influences the entire manufacturing process. The wrong agitator can increase reaction time, create temperature gradients, damage crystals, reduce heat transfer, and even lower product yield. Let's look at a few real engineering scenarios. Imagine a hydrogenation reaction. The reactor is operating at the correct temperature. Pressure is normal. The catalyst has been charged. Yet, the reaction is progressing much more slowly than expected. Many engineers first suspect the catalyst or reaction chemistry. But the real issue may be mixing. If an anchor agitator is used, it provides very little gas dispersion. Large hydrogen bubbles rise quickly to the surface without dissolving efficiently into the liquid. As a result, gas-liquid mass transfer becomes the limiting step. Replacing the anchor with a Rushton turbine creates much finer gas bubbles, improves hydrogen dispersion, and significantly increases the reaction rate. Sometimes, the chemistry isn't the problem. The mixing is. Now consider a cooling crystallization process. The objective is to produce large, well-defined crystals. But instead, the plant produces excessive fine particles. Filtration becomes slow. Drying takes longer. What happened? The agitator generated too much shear. As crystals grew, they continuously collided with the high shear zone near the impeller and fractured into smaller particles. Using a retreat curve impeller, or another low shear design, allows crystals to grow with much less breakage. The result is larger crystals, faster filtration, and shorter drying time. Now let's look at another common plant problem. A neutralization reaction is carried out in a large reactor. The bulk pH appears normal. Yet the laboratory reports an unexpected impurity. How can that happen? The problem is often poor circulation. When sodium hydroxide is added into the reactor, it doesn't instantly mix with the entire batch. If circulation is weak, a highly concentrated pocket of NaOH forms near the addition point. For a few seconds, the local pH can become much higher than the average reactor pH. That localized high pH region may trigger unwanted side reactions, leading to impurity formation. Using a pitched blade turbine provides strong axial circulation, rapidly dispersing the added NaOH throughout the reactor and minimizing local concentration gradients. In many semi-batch reactions, good mixing isn't just about faster blending, it's about protecting product quality. Now imagine manufacturing a polymer or pharmaceutical cream. As viscosity increases, a conventional turbine agitator becomes less effective. Only the liquid close to the impeller moves. Material near the reactor wall barely circulates. Heat transfer slows down. Some regions become hotter than others. This can affect product quality and make the batch more difficult to control. Replacing the turbine with an anchor agitator restores wall circulation and improves temperature uniformity. These examples highlight an important lesson. Experienced process engineers don't select an agitator based on habit. They first identify what controls the process. Is heat transfer limiting the reaction? Is gas-liquid mass transfer the bottleneck? Do solids need to remain suspended? Will crystals break under high shear? Will viscosity increase during the batch? Once these questions are answered, the correct flow pattern becomes clear. And once the flow pattern is clear, choosing the right agitator becomes a logical engineering decision. Let's see if you've started thinking like a process engineer. You are manufacturing a high-viscosity pharmaceutical cream, and efficient heat transfer is critical. Which agitator would you choose? Don't just tell me the answer. Tell me why. I hope this episode helped you understand how engineers select the right agitator and why the choice goes far beyond simply mixing a liquid. If you found this video useful, please like, share, and subscribe to PharmaChemE. Your support motivates me to create more practical engineering content for the chemical and pharmaceutical industry. In the next episode, we'll take this one step further and explore how agitation is scaled up from the laboratory to commercial production. Because selecting the right agitator is only half the challenge. Scaling it up successfully is where real process engineering begins. Thanks for watching, and I'll see you in the next episode.